Hi kids, this important lecture is on equation building, which is a skill we'll be using throughout the entire year, and the relationships that we use to help build our equations, including direct and inverse relationships. In general, relationships describe what happens to one variable when we change the value of another variable. So there are two relationships that we'll cover in this class this year. The first is called a direct relationship, and this is when increasing the value of one variable increases the value of another variable by the same percent. Likewise, decreasing the value of one variable decreases the value of the other variable by the same percent. For example, the number of shoes in this classroom and the number of people in this classroom. If I double the people in the classroom, I'm going to double the shoes. If I halve the number of shoes in the classroom, I did that by halving the number of people. You'll note that it isn't like a numerical change. I wouldn't say I added 6 people and therefore I added 6 shoes. That isn't how it works. It is all about percentages and ratios. You could also use this for kind of fluffier things like jelly beans and happiness. If you get more jelly beans, you get happier, and if you get less jelly beans, you're going to be less happy. When you have two variables that share a direct relationship with each other, it means that when you make an equation, you'll have one variable on one side of the equation and the other one on the numerator on the other side of the equation. This way, if you multiply the variables on one side of the equation by a factor, so if I multiply the left side by 2, for example, it's going to have the same effect on the right side. The right side would be multiplied by 2 in order to maintain the balance of the equation. If you had an ideal data set with perfect data that showed direct relationships between two variables, you'd see something like this. So for example, if you know that 2 people have 10,000 hairs, when you double the number of people to 4, we now double the number of hairs as well, right? 2 times greater. If instead of doubling we tripled to 6 people, then my hair is going to triple as well. We're going to have 30,000 hairs. Same thing if we quadruple. You could also look at this in reverse. If we start off with 8 people and we quarter the number of people that we have, go from 8 to 2 people, well, the hairs are going to quarter as well, going down from 40,000 to 10,000 hairs. Real data seldom looks as neat and tidy as that data did. Instead, it's a little bit harder to see direct relationships if you just write your data down. So for example, this jelly beans happiness data set, hopefully you see that there is some sort of trend. As jelly beans increase, happiness increases as well. But it's really kind of hard to tell if it is that direct relationship where doubling one roughly doubles the other as well. So when you have a hard time telling what's going on with a data set, the best way to simplify and clarify what's going on is to graph it. Often when people take their first shot at a graph of data like this, it looks kind of like the graph that's shown. You put the 4 data points on, but then often people are connecting those data points with lines. Those lines don't really have any meaning or any basis in fact. In fact, if you tried to look at it for this graph, it would say that your happiness increases a lot more with the first, from jelly bean 1 to 2, and then increases a lot from 3 to 4, but doesn't really increase that much from 2 to 3, and that really just doesn't make any sense when you think about the physical scenario. It should be sort of a constant slope or a constant change in happiness as we add jelly beans. So instead of connecting the dots in a data set, I prefer that when you make a graph of any data in this class, you use what's called a best fit line, or a trend line. And that trend line is a line that you draw through the center of the data points. You're not trying to pass through the data points, you're just trying to represent the overall trend that you see in your data. Now that trend line is much more accurate than connecting the dots, and it allows you to make predictions about the value of unknown happiness jelly bean values. For example, if I was interested in, what would happen, how happy would you be with 2.5 jelly beans? Well, we didn't take any data for that, but I could find that point on the graph and make my guess about 25 jelly beans, I would say, from the graph. The other relationship that we use a lot in this class is called an indirect relationship or an inverse relationship, and it's sort of the opposite of a direct relationship, where increasing the value of one of the variables decreases the value of the other variable. So for example, if one variable doubles, the other one halves, or if one variable triples, the other one is multiplied by 1/3. That's a reciprocal or an inverse relationship. At the same time, so if you decrease the value of one variable, you're going to be increasing the value of the other. There's examples of indirect relationships in your lives as well. For example, the distance your car has driven and the amount of gas that's remaining. The further you drive, the less gas you have. The more gas you have, probably the smaller of the distance that you have actually driven. If you try to build an equation, or you using an inverse or indirect relationship, you'll notice that the variables are on opposite sides of that equal sign, and one of those variables is going to be on the denominator, on the bottom of the fraction on the other side. This is because as the denominator of a fraction gets large, the fraction itself gets small. 1 divided by a large number is a really small number. So when g is getting bigger in this equation, it's actually going to make the value of d go down, which is what we're expecting in an indirect relationship. I should have mentioned earlier what these little x's were for. Those are basically to show you that this isn't the entirety of the equation. There might be other stuff in the equation than just the variables we're talking about. There might be other variables that matter as well. And it's kind of a placeholder for those other variables. So you saw that a couple slides ago and also in this slide. If you know that two variables are inversely related, like g and d, you could write it d equals 1 over g, or you could write g equals 1 over d. Those are the same mathematically. You can actually solve both of those equations the exact same way, and they mean the same thing. If you were looking at an indirect data set, you would notice that when one variable doubles from 2 to 4, the other variable halves. We go from 10 to 30, so times 2, and this thing is 1/2 as big. If we go triple something, right, from 2 to 6, the other variable is going to become 1/3 as large. And if we did the reverse scenario where we go from 8 to 2, so we're becoming 1/4 as large on the x side, well, you'll notice that on the y side here, we are going to get 4 times bigger, which is the reciprocal or the inverse of 1/4. If you graph the data set, the inverse relationship data set, you'll notice that it's actually a curved line. That's because the values in an inverse relationship can never reach 0. They can approach 0, but if you take a number and have it over again and keep taking half of it, you still end up never quite getting to 0. You keep getting smaller and smaller values, but it's actually called an asymptote. This thing gets closer and closer to 0, but doesn't quite actually ever reach 0. Same thing on this side. Each time you have the x value, you have to double the y value. So we end up shooting up way straight up high there, and never actually reaching that y-axis, although it does approach it. So we have an asymptote there as well. So in general, if you have an inverse relationship on a graph, you expect to see this curved shape on the graph instead of a straight line like we saw with direct relationships. So once you have your individual relationships, you can actually combine several individual relationships to make an equation. Let's say that one variable, h, has relationships with 2 other variables. You might have a direct relationship with j or an indirect relationship with w, and no other variables affect it. when I was writing this, I was thinking H might stand for happiness, J might stand for jelly beans, and W might stand for war. In other words, the more jelly beans I have, the happier I am. The more wars that are out there in the world, the less happy I am. And maybe I don't care about anything in this world except for jelly beans and war. So if you look at the two individual relationships, we know that H has to be on one side of the equal sign and J has to be on the numerator of the other side. And I know that H has to be on one side of the equation and W has to be on the denominator of the other side of the equation. So if you take those two relationships, if they're the only two things that affect H, you can smush them together and get an equation which contains both of those relationships. And the equation you would get is H equals J over W. Now that we have this equation, we can actually use it to make predictions about how changing the values of one of the variables affects the other. So, what happens if you double J? Well, J has a direct relationship with H, so doubling J should double H. What happens if instead you triple W? W has an inverse relationship with H, so tripling W should cause H to go down by a factor of 1/3. And what happens if you quadruple both J and W? Well, quadrupling J makes H go up by a factor of 4. Quadrupling W makes H go down by a factor of 1/4, and those are going to end up canceling each other. 4 over 4 cancels out, and you end up just not affecting H. H is the same happiness that you had when you had your original single jelly bean and single war, or whatever was involved in your original scenario. So let's try a little bit of a harder one. Assume there's a variable called do, and it has 5 direct relationships with the variables S, T, A, and D, N, and D, and it has 1 indirect relationship with the variable U. Can you write the equation? Hopefully the answer is yes, but if you need help with this, if you're struggling to understand or to follow along, please come see me at tutor time or any other time, as this will be something we'll be using throughout the entire year. Thanks.